into it.
Great. Welcome to Cassandra Lunch. Oh, wait, I've got to start my screen share here. Welcome to Cassandra Lunch, number 105. I'm here with Ricardo Rosales, and he's getting ready to share his presentation and demo around an extremely exciting tool. His presentation is entitled From Raw Events to AI Application with hey, how do you pronounce the name of this service?
We call it Aineko.
Aineko, great.
Yeah.
Aineko is an open source Python framework that makes it easy to build event-driven AI applications. Aineko provides a simple interface for connecting to event sources, processing events, interacting with AI models, and serving results while ensuring that the resulting applications are massively scalable. The co-organizers for this event are Rahul and myself. If you are interested in being a co-organizer and want to help get speakers by reaching out to people in the Cassandra community, or the data engineering community around the world, drop me an email. It's listed below right there. You yourself are interested in giving a talk at Data Engineers Lunch or our sister lunch, Cassandra Lunch, please feel free to reach out to me. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, generally centered around data. And you can find out more about all of the different groups and events at datacommunitydc.org. What do we cover here at Data Engineers Lunch? We cover all things data sources, data engineering, and user experience, from the ingress to egress of data and everything in between. Welcome, everyone. If you'd like to say hi, what brought you here, what you hope to get out of this, please drop something in the YouTube chat. And don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. A few rules. If you have a question, please ask it in the YouTube chat. I will be handling these questions towards the end of the session. Please always be polite and courteous to others, and share what you know with us. Thanks to our sponsors. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. So data engineering is our bread and butter. We also can tune a mean LLM. Thanks to all of our sponsors, DataStax, George Washington University, and our institutional and organizational sponsors. If anyone has job offers or you're looking for a job, please drop links in the YouTube chat and we will that'll help broadcast them. Additionally, if there are any meetups, hackathons, classes, conferences that you would like to promote, feel free to post those links as well. We currently host Cassandra Lunch, our sister lunch on Thursdays at 1 o'clock, at noon Eastern. We host this Data Engineers Lunch Mondays at noon Eastern. And you can always view them on YouTube. We have a series of runbooks that are available for Cassandra that are available to download. The most recent, Cassandra runbook number 17, is available for free. You can access the rest on your own time. So with that, I want to thank Ricardo for being here, and I'm going to pass the baton to him.
Thanks, Nick. All right, let me go ahead and start the screen share over here. Okay, cool. So today I'm going to present a presentation that I put together called From Raw Events to AI Application with Aineko. So before I dive in, I'll just give a quick introduction about myself and what it is we're trying to build at Aineko. So I originally started my career as an AI researcher, did a lot of work in an area of that we now call AutoML, but of hyperparameter optimization. I tried to start a company in that area, didn't quite work out, so I sold out. Kicked off my career wrangling robots in Wall Street. So I was a high frequency trader for a while, and I worked on at a hedge fund managing a global algorithmic trading desk. After doing that for a while, decided that I wanted to move to the West Coast and start working at a startup instead. Worked in and around the ecosystem, and eventually decided to start this company. So Aineko was started with the goal that we've seen a lot of folks build different data platforms, and we wanted to basically lower the barrier for people to use data in their organizations. So today, basically what I want to cover is I want to talk a little bit about event-driven AI, discuss some of what exactly that might mean. I want to go over some best practices for building with event-driven AI, talk a bit about the Aineko framework and how it applies to building these types of applications. I'll show you all a demo, and then I'll make sure to leave enough time at the end to go over some questions. So first and foremost, event-driven AI. So from the perspective of a data team, basically, event-driven AI is a software architecture paradigm that frames problems as a series of processing steps with input and output data. At the highest level, an application built using EDA or event-driven architecture takes as inputs events from event producers, and it emits results to results consumers, right? So basically, you get events from some source, and you want to consume them, and there's some code that happens in the middle. Event-driven AI is about adding a touch of magic to the processing that happens in the middle, right? So enabling more automated and intelligent behaviors in the types of applications that you can create. So the reality is that under the hood, for building these types of applications, there's a lot of bits and pieces that you have to put together. You have to think about constructing a data layer that might involve message brokers so that you can distribute efficiently data across the system, databases so you can cache information and make it available for processing downstream. You also need to build a compute layer that allows you to distribute compute in an efficient manner and also manage stateless and stateful computation. And then you need to build an intelligence layer, which allows you to integrate with models and other AI intelligence services to basically get the insights or get those intelligent behaviors, automated and intelligent behaviors that we were discussing. On the left-hand side, there's a plethora of event producers that are out there. When we structure building event-driven applications, basically, as input, you can consume data from a data store, maybe change updates that are happening into a data store, images that are being written to an S3 bucket, anything of this sort. You can consume events from API servers. So whether they're the servers that you're running yourself or servers that are being managed by third parties. You can hook it up to event trackers. So these might be things like a customer data platform or even website analytics or something like that. There's also time. There's a lot of applications that you kind of want to run scheduled sort of crons and activities that are generated by or emitted based on time. And then there's other devices, right? So there's these edge devices, whether it's browsers or cell phones or so on, IoT devices that emit data and translate it across the internet. The results consumers can typically be anything from third-party APIs that you might want to take actions on, application endpoints that you're managing to basically surface the results of these these applications that you're building to downstream applications. UIs making the insights available to dashboards or otherwise available inside of user interfaces. Or even pushing data to data warehouses such that it's available for processing at a later time. In addition to all that, you eventually need to push these events or the results of these events and logs and so on for so that you can maintain this for monitoring and alerting. So you might ask, like, what's the point or why we would even want to go with an event-driven architecture to begin with. For those familiar with or some experience building with event-driven architectures, you probably know that the primary benefits are around reliability, responsiveness, and scalability, right? In an event-driven system, failure in one component does not necessarily bring down the whole system. This isolation improves overall system resilience and uptime. By dealing with events individually, it's often easier to identify and handle errors and to implement robust retry mechanisms for failed event processing. With respect to responsiveness, in applications like gaming, real-time analytics, UIs, event-driven architectures allow for immediate dynamic responses for user actions, leading to a more interactive and responsive user experience. Event-driven systems are particularly beneficial for applications where user experience is paramount and requires immediate updates based on user or system interactions. When it comes to scalability, event-driven architectures can handle varying loads efficiently. Since components are loosely coupled and only react to events, it's easier to scale parts of the system independently based on demand. Event-driven architectures also inherently support load balancing. As events are generated, they can be distributed across multiple handlers or services, thus efficiently managing the load. So after building many of these types of applications in the wild, our team started to recognize that there are some additional benefits that are not always super obvious. So one of the things that we found is that it's easier to reason about problems when thinking about them as processing events in a series of steps, as opposed to monoliths or service-oriented architectures. The patterns involved in event-driven architectures more closely represent real-world processes, and explicitly defining inputs and outputs simplify understanding of data flow, right? So creating these types of applications actually represents more like what you might think of in the real world, right? Like ordering a hamburger at McDonald's. You imagine that that order gets received by some person on the assembly line. That person puts down the patty and so on and so forth. A series of events occurs until you drive up to the window and receive your burger. We've also found that introducing feedback loops into event-driven architectures comes naturally. So specifically with event-driven AI, the ability to capture production data and use the inputs and outputs to improve performance over time is a huge unlock, given the difficulty in acquiring high quality data sets and the importance of that quality data sets for building machine learning applications. Additionally, loose coupling not only helps make event-driven applications more reliable, it also means that introducing new features is a matter of adding a new input and output steps, or modifying a few of the steps without necessarily having knowledge of the entire system. Lastly, we found that similar to service-oriented architectures, event-driven architectures also inherit a natural mechanism for scaling to zero. So since individual processing steps are idle until triggered by an event, unused resources are returned to the machine, to the system that they're running on, and scaling individual processing steps does not add additional overhead. So maybe we're convinced that building using an event-driven architecture, particularly with AI, might be a good thing. The reality is that when you go to put these into production, there are tons of implementation challenges that you have to face, right? So first off is infrastructure, right? Implementing event-driven architectures requires that you design an efficient event processing pipeline that minimizes latency, ensures reliable message delivery across distributed systems, and manages the complexity of stateful and stateless processing. In addition to all that, we have to think about integrations. There's a challenge in integrating heterogeneous data sources and ensuring AI model accuracy in the face of rapidly changing data. All that said, you also face a challenge around maintenance. Maintaining a system, scalability, and resilience, particularly during high demand periods, poses significant engineering demands and requires specialized tooling to maximize observability and control. So let's talk about a couple best practices for building these types of applications, and make sure that if you want to build with this architecture, you get unstuck. So first off, I would suggest to embrace the modularity. To get the full benefits of an event-driven architecture, it's important to embrace the modularity that comes inherent in these types of systems. It seems tedious at times, but breaking down a problem into the smallest possible steps leads to the biggest gains in the future. In addition to that, I would suggest to embrace real-time. A common mistake we see is teams reverting to old patterns of batch processing while building in an event-driven architecture. While applications may not always require ultra-low latency responses, processing events just in time leads to other benefits as well. For example, upstream failures are recognized early and patches can be made to process all of the unprocessed data, right? You get an additional piece of time if you process things just in time, as opposed to waiting till all of the data gets completed and running in a batch. So all that said, I would also suggest that you don't try to reinvent the wheel. Overcoming the implementation challenges we presented earlier becomes insurmountable when you try to hand roll your own solution. However, currently, there are many open source tools that have been introduced over the past decade that make these challenges a lot more palpable. So here are a couple of the tools that we've encountered out in the wild that make dealing with event-driven architectures and building event-driven AI a lot easier. When it comes to message brokers, we particularly like Kafka as a very scalable system for distributing messages across a distributed system. RabbitMQ also serves the purpose in a lot of cases, and there's also an open source tool called Celery that kind of can help along these lines as well. When it comes to distributed compute, typically we see folks either hand rolling a lot of solutions on top of Kubernetes, interacting with something like Ray, which is built as a Python native distributed computing framework, or something like Flink that makes unify sort of stream and batch processing, and is a very well kind of regarded project in the Java community. In addition to that, there are a growing number of AI model integrations that we can build on top of now. When I first started working with AI, it was all about building kind of your own solutions and coding directly onto GPUs. But nowadays, you can take advantage of open source models on Hugging Face. You can take advantage of paid models on OpenAI, or even spin up your own models using something like PyTorch, and the interfaces have improved significantly over the past couple of years. So let's talk a little bit about Aineko now. So Aineko is all about trying to get an event-driven AI application into production. So first, you might ask, what is Aineko? So we got a brief introduction before, but at a high level, Aineko is a framework, a Python framework that makes building data processing pipelines super easy, right? In addition to that, Aineko is an open source. So the open source framework allows you to, on your laptop or whatever in your local environment, rapidly build a prototype and iterate quickly. In addition to that, we have developed a cloud product where if you develop an application that utilizes the Aineko framework, you can bundle all of your pieces together and automate deployments, push them to the cloud, and not have to worry about any of the underlying infrastructure. So here's a bit at a high level of what some of the architecture for Aineko looks like. So inside of Aineko, you get a lot of neat things for free, but what you have to provide as a user is effectively code, right? So this code represents the units of compute, the processing steps that are required to move from a data to a processed event to processed data to results and so on. You provide an application manifest. The application manifest effectively represents the topology of the application, tells us a little bit about how you want to combine your compute assets with data assets and how you want data to flow through the system. In addition to that, you have to connect your own events, right? So these events, whether they're from third parties, whether they're from other systems that you manage, or potentially other Aineko applications as well. In the middle, we provide a few abstractions that make it really easy to put all of these pieces together. With Aineko, you can develop using pre-built connectors, model integrations, and API integrations, and so on. Build a library of compute assets that you can plug and play together for the particular needs that you might have. This makes it really useful to collaborate inside of a team, both because a team can focus on building one compute asset, a class of compute assets, and otherwise take advantage of the compute assets that are built by other members of the team. In addition to that, you can represent your data assets. So these are all the messages that flow through the system, and all the way going from raw data to process features to the results that you're generating. And you can decide in the Aineko framework whether you would like the data to be ephemeral, as in just messages passing through through distributed compute, or otherwise, if you want to have long-term storage for particular data records that you're producing. We abstract away kind of two best-in-class projects, which I discussed earlier, Ray and Kafka. So Ray and Kafka really allow us to spin up a service for running these types of applications that make it that abstract away everything required to distribute computation across multiple processes on one system or across multiple nodes inside of a distributed system. And Kafka basically allows us to make sure that we have a hardened system for distributing data across this, all of the processes that might be operating on that data. So an Aineko application is really just a combination of what we call nodes and data sets. So nodes are just these units of compute, these compute assets that you piece together, and data sets are just these data assets that you piece together. Nodes can represent anything that you can write in Python effectively, which means that you also get a lot of nice integrations leaning on the open source contributions that folks have made to the Python community for the last couple of decades. So in addition to that, the data sets you represent, like I mentioned before, can be basically ephemeral or long-term data sets. And the way that the application, the data flows through the application is just a function of basically the inputs and outputs for nodes. And inputs and outputs for nodes are basically all data sets in the context of an Aineko application. So what you get from all of this is actions or outputs, right? So these actions are basically actions that you take in third-party systems or in other systems that you manage. So imagine, you want to send a notification as a result of an event that has occurred. You want to update a database as an event that hasn't occurred. Or perhaps, you want to take an action on an external system. Like, for example, for my old world, you might be consuming market data, have some algorithm that is telling you when to buy and sell stocks, and the action you take is to trade a stock on an exchange or something like that. So the goal, like I mentioned before, is all about getting to prod. So we want to get to production as quickly as possible without losing a lot of brain cells. At Aineko, that's the main mission that we have is to ensure that data engineers and data teams retain all the brain cells that they have. So from a build perspective, we offer Aineko open source, like I mentioned before. The current features are all about embracing modularity, making sure that you have that modular compute. I'll show you all in a moment how you put those pieces together. Having first-class stream support to ensure that you can do stream processing in an efficient manner in a scalable way. Having this composable module library that allows you to pick and choose, what nodes you want to put together. Sub-millisecond latency, when processing, when shipping data from one node to another, and interactive local runs. This is kind of huge. From the users that we've had so far, we've seen developers get a lot of benefit from being able to run in a pipeline end-to-end locally, iterate, take the pipeline down, rerun the pipeline after making a few changes, seeing the whole result live, right? Getting those iterations makes the development process a lot faster. In the future, we want to focus on sort of optimized data indexing to ensure that we're able to query data very quickly, very efficiently for all the use cases that we want to cover. Schema validation is something that we're working on right now to ensure that as data flows through the system, error handling and so on can be a bit more automated. We want to support more runtimes. We want to create replayability out of the box, and maybe in the future do something like multi-language support. Within Aineko Cloud, this is all about after you want to ship. You want to get to production, you get to production, you ship to the cloud. Currently, we support fully automated deployments. All it takes is pushing a change to GitHub, making a commit to GitHub, merging a PR, and you have all new infrastructure that's running, that's representing your application. We do allow we have a generative templating tool that that allows you to onboard to the system a lot more efficiently. We allow for CI/CD workflows to ensure that it fits directly into the patterns that you already have with development. Full observability of all the applications that are running, logs, monitoring, alerts, and so on, and isolated environments. This is super important. Big important thing when running these types of applications is privacy and security. And creating these sort of isolated environments ensures that developers can build with peace of mind that their data is secure, and there won't be interactions that they don't want to exist. Things that we're working on adding now are things like full end-to-end integration tests. We think based on the framework that we've built, we have the ability to do live integration tests using production data or simulated data for end-to-end applications. We already do some of this with our internal use cases, but we want to expose this capability to our users. Data lineage is something that you can do sort of manually currently using the Aineko framework, but we want to make this a lot more explicit and the user interface to be a lot neater for users. Self-hosted deployments. Currently, if you develop an Aineko application, it basically becomes a Docker image that you can sort of deploy on your own if you'd like. But we want to expose the deployment pattern that we use internally to manage the Aineko Cloud to external customers as well. Other things that we're going to be working on in the near future are things like canary deployments to ensure that as you're sort of moving for environments, moving from versions, that you can do that in a neat fashion. And then also data governance to ensure that you keep a tight control over how data moves through the system and what becomes available and not to certain counterparts. So how to use Aineko? Currently, the way that you use Aineko is you start with a sketch. So the sketch basically looks like everyone here, or a lot of you must be familiar with the concept of a DAG, right? So directed acyclic graph. Within Aineko, think of it more as just the graph. So you can actually have cycles inside of the graphs because the compute that is happening inside of the nodes can be both stateless or stateful, in which case, having cycles like this is something that becomes relatively straightforward to manage inside of the Aineko framework. You build your sketch using, something like a graph, and then you create your project, and you can run the application directly from your terminal, as I mentioned here. Once you're ready to sort of expand the use case, expand the capabilities of your application, you write node code in Python. The node code is simple framework that will be familiar to any Python developer, and we have no limitations on the types of tools that you can utilize. You can program in an async manner, in a synchronous manner. You can use whatever ML tools you'd like. You can expose ports to the outside internet. You can do all sorts of things that you might want to do and that you have the ability to do inside of a Python application. You can configure data sets. So the data sets are really just a simple YAML file that describes the type of data set that you want to provision, that you want to have available to your pipeline, and maybe some configuration around it. The typical use case here is a Kafka topic, right? So you would have a data set that is represented under the hood by a Kafka topic, but you can have available to you all sorts of other data sets as well. And this is a growing kind of area for us where we want to support more and more sort of data formats in the future out of the box. So the last thing that you do is define the application topology. So I'll show you all an example of this a little bit more in detail in a moment. But the gist is, again, it's a simple YAML file that represents the input and output or the series of nodes that you want to include as part of your pipeline and the corresponding input and output data sets. The last thing that you do is push to the cloud, right? So like I mentioned before, this is as simple as committing to GitHub and pushing to GitHub. So we have a notion of a deployment branch versus a feature branch. So if you push to a feature branch, you will only get sort of CI to kick in on our backend. So we will validate your project to make sure that everything's running as expected, and then or everything would run as expected. And then when you push to a deployment branch, then or you merge PR into a deployment branch, we actually go and generate infrastructure or go and take a look at the state of the world of all of the infrastructure that you're currently running and operate on any diffs, right? So if we need to provision a new compute infrastructure, new data set infrastructure, and so on, in order to make sure that the application that you've represented is, or that you've represented as part of your application topology is correctly reflected. So I'll go into a little bit of a demo. So to show you a bit more of what you can do with Aineko. So the demo that I'm going to show is an internal tool that we created called Aineko Dream. So Aineko Dream was basically started as an internal hackathon project at the company, where we wanted to make onboarding to the Aineko framework more straightforward. So what we wanted to do was basically create an entire Aineko project from a prompt, right? So you could say something like, build me a project that ingests logs from Datadog and processes them in some way, shape, or form and makes them available via an API, right? So if you did that, then Aineko Dream will effectively create the YAML files that are required to kind of put the pieces together, all the input and output data sets, and take a pass at the processing logic, the Python code that's required for each of those snippets. So how this looks under the hood, this is a little bit of a simplified version of the way that the pipeline actually looks, but you might say, to Aineko Dream, something like generate an Aineko pipeline code from a prompt, given sort of the example that I gave before. So on one hand, in an Aineko node, we run a fast API server. So you can run a fast API server inside of an Aineko node to sort of expose an endpoint that will allow you to get data into the into the pipeline, or otherwise push data out of the pipeline as well. In addition to that, we have this docs fetcher. We call it the docs fetcher node. Effectively, what this does is it's subscribing to a GitHub webhook that whenever there are changes to the Aineko framework, it will, to the docs for the Aineko framework, it will fetch all of those docs and update the docs to make it available for the prompt that will be utilized to create the project. The prompt that is given by a user is combined with both the updated docs, the sort of live stream of updated docs that are coming in from GitHub. And in addition to that, we have a process that goes through and consolidates, aggregates examples of other Aineko pipelines that are out in the wild that we've built, that other developers have built, and so on, and combine them into a vector database and make them available for retrieval augmented generation. So the prompt enricher node really just takes the prompt from the user, the updated docs, and sort of the examples that come from the vector database, combines that into a single prompt, an enriched prompt, let's call it, and sends that to a large language model client. In this example, and for our case, we use OpenAI, pretty straightforward to use. So we've gone with that, and it's relatively well performant for the use case that we've had so far. You send the request to the OpenAI client, and you receive back a model response. That model response then gets injected or gets passed on to what we call a response evaluator node. The response evaluator node basically takes a look at the code, runs some checks, maybe validates things like, is it validly part of the Aineko framework? Well, basically, can we execute it as an Aineko application? Maybe does something like, is it valid Python code, right? Will it actually execute as Python code? And then stuff like security, things like maybe do a security scan to make sure that there's no security concerns with the code that's been written. But you can imagine having any series of evaluations that you might do at this level. And there's a bunch of different ways to sort of treat this. One option is that you can just stop here and say, I'm done, if there's an error. But what we found to be useful is that if an error is found, you can basically take the result from the response evaluator and pipe that back into the enriched prompt so that you can pass a message back to the OpenAI client with all of the original messages and basically kind of continue the chat and say, hey, this result that you gave me had the following errors, please fix it. And we find that in most cases, convergence will happen even just in after 2 requests effectively. Once you get a valid response and it passes all of the checks, you get the final response, gets sent back to the Fast API app, and the output gets emitted somewhere. In our case, we do a couple of interesting things. Not only do we pass the result back to the user, we also put the result on GitHub so that it's available for users to create, to basically use as a template inside of their future environment. So let me show a bit of what this looks like here. So the this is what like a typical pipeline configuration file looks like. So this represents the topology of the pipeline, like I mentioned before. So we talked a little bit about this GitHub doc fetcher, right? So in this case here, we call our node, we give our node a name, and then we point the name to a class that represents the code that will actually do this execution. So you'll notice that this basically just follows the path. I'll show you the code in a moment. Basically in the Aineko Dream folder, there's a file called nodes. Inside of there, there's another file called fetch docs. And then inside of that, there's a class called GitHub doc fetcher. So we'll look in a moment, nodes is here, fetch docs, and here's the GitHub doc fetcher. In this case, this is a production version of this program. So it is, it can be relatively long, but you see that through a series of relatively simple, setup and processing, you consume a GitHub event, and then you process it using the logic that you have under the hood here. In this case, we just want to check that it's valid. It's part of the organization and repo that we care about. We want to make sure that it's like part for the right branch that we're trying to monitor. And then based on that, we do some processing to take the raw data and turn it into something that will be legible by the large language model. So if we go back to here, similarly, you can, or actually let me show here, the input is this GitHub event, right? So this is a data set that's storing all of the events that are coming back from GitHub. So this is all of the, a push, a PR, a commit, or something like that shows changes to the files that are happening under the hood. And then the output is a data set called document. So this data set is basically just emitting the document, the freshest document based on the changes that are happening in GitHub. And then we have a feature that allows you to pass in parameters so that you can make your modules even more modular, right? So in this particular case, we pass in the organization Aineko dev, the repo Aineko, and the branch develop. But you can imagine that now that we've written this, if you want to do the same sort of setup of fetching documentation for a different project, all you'd have to do is change the organization, repo, branch, and so on. We also, kind of expose this ability to parse only certain file paths. This is useful for the models that have a lower, token range. But in the case of some of the larger models, you can kind of parse as much data as you might have. This is the prompt model node, the GPT client node. So you see here we're using the GPT-4 model with a certain amount of tokens, and here's our temperature setting, and so on and so forth. You get all of the corresponding kind of input and output steps. The typical, let me see, maybe let's go with this one. Should be pretty easy. No. Here we go. Maybe this is straightforward enough. So the typical Aineko node code is represented by a class, especially if you want stateful computation. When you put together an Aineko class, all you need to do is inherit from this abstract node class that you import from the Aineko package. In that, we have basically two requirements, or actually only one requirement. The one requirement is that you implement this execute function, this execute method. An additional option that you have is to implement what we call the pre-loop hook. This is basically just code that runs before the process actually kind of starts spinning. So this is just setup, right? So setup if you want to initialize the state, let's say, of the class, right? It would behave similar to like what the init method might do, but this is specific to developing the Aineko framework. The execute method basically just runs and operates on the data that's being processed, right? So we give you the ability to import data or ingest data from specific data set. In this case, we're ingesting from a data set called LLM response, and we're going to consume the next data point at each side. So it'll basically lock until it gets a message and then move on to the next one. And then you can just put in all the kind of logic that is specific to the to the example that you have at your disposal. So maybe, I should have probably ran this first, but the way that we run things using Aineko is, so I use Poetry to manage things. So I'll use Poetry run here, but I'm going to run service start. So this will basically just start all the background services that are required for Aineko. In this case, you see we're basically running a zookeeper and a broker. This is effectively just to manage Kafka under the hood for us. So kind of knows that we want to build a data set using Kafka, so it'll get that started. And then we can run, Poetry run Aineko run com and pipeline. So this is the I'm going to reference the pipeline.yaml file, right? That represents the topology of the application we discussed earlier. And I'm going to run that. So as you see now, when the application starts up, we first create a couple of the data sets. So here it tells us, okay, we're going to create a data set called template generator.github event. And the type is a Kafka stream, right? So these are all Kafka streams in this particular case. We create all of the data sets that we configured inside of that file. And then we start to get some additional messages. We set up Ray. We talked about Ray and how that helps us manage distributed computing. So that we get that started. And the fast API node sets up and starts to run the server on this endpoint here. And we see that when the prompt model node started, it basically right now it's starting the vector database from scratch because it's a new part of my system. So it's ingesting all of those examples that I described, starting a FAISS database and loading all of those examples in there with using the OpenAI embeddings. So now that the server's running and everything's going, maybe I can go over here and create an example. So we can basically give it whatever we want, but maybe I'll update this to something new so that we can all see it working live. So maybe I'll say Aineko dream. Maybe we'll go with the example we talked about earlier. And just let's do synthetic logs just so we can see what that looks like. Ingest a synthetic log stream and process it using an AI model. And I'll just tell it maybe use 3 nodes total, just to like maybe give it a additional parameter here. So I'm going to run this. Well, you see here that okay, I'm referencing, if you notice, my local machine so that I can reference the local version of what's running. We're generating this here, and you see over here that we got an additional update here. This is basically stepping through this approach here. So the fast API node is accepting the prompt, passing that to the prompt enricher, basically retrieving the examples that are required, creating that enriched prompt, launching it to the OpenAI model, the OpenAI client, receiving the result and running the evaluations. It takes a little bit to run based on kind of the complexity of what's happening, and also doing a cold start on OpenAI. So while that's running, I'll go into this. So basically, one of the other things that we can do here is, let me go back to, oops. So we have a tool called Visualize that allows us to visualize the topology of this application. As you see, I showed a very simple example, but the actually what's in production is quite a bit more complicated, especially because we're doing some retry logic and handling errors and all of this type of stuff. But doing all of that becomes very explicit within the context of this application. You can see the whole the data flows through inputs and outputs throughout this whole thing. The orange circles here are basically just the units of compute that we described, and the blue are the data sets. The other thing I'll show quickly is this is Aineko Cloud. So basically, the current version of Aineko Cloud is just set up as an observability tool that allows you to see everything that's happening in production and that you've sent to the cloud. Right now, for this particular project, which is Aineko Dream project, so we have a version of this running in production. We have one active pipeline. That pipeline has 11 nodes. We're running it in one environment. And we have one healthy pipeline and one inactive. You'll see in a moment, basically, we have a production environment that's currently down. And you get some metadata here. In addition to that, we can see the environments. Like I mentioned, the production environment is currently inactive. I can click in here and see the pipelines that are running in this particular environment. I can toggle here. I see that the template generator pipeline, which is the one that I'm running locally, is also running in the cloud. Another neat thing here is the workflows. Like I mentioned before, as you push changes to GitHub, we basically ingest those changes that are coming from GitHub and launch workflows. The typical workflows, like I mentioned, are the CI workflows, where we basically just want to validate the deployment. We just want to check that the code that you've uploaded to GitHub and the corresponding application and deployment configuration will lead to a valid deployment, right? After that, we can do this. Maybe let me give an example of one that completed. Here we go. So there's a CD job. In addition to validating the deployment, we also give the user the ability to approve the deployment. So you see here, we actually have one that's on hold. So this one that's on hold just gives the user the ability to make a speed bump, right? So you want to push to production, you want to just double check everything to make sure everything looks good before changing any of the infrastructure. We give that approval step. We build and push the image. Like I mentioned, when you create an Aineko application, you really are just creating a Docker image. So we build that image, we upload it to a container repository, and we push that. Then we deploy the infrastructure. All the infrastructure gets deployed. We pull down the image and basically run that and see it live. I think the logs, there might not be any logs on this particular pipeline because, oh, here we go. So there's a few logs. So you see, we successfully uploaded a file to GitHub. It looks like we did have a couple of logs from a run that happened actually this morning. We have a couple of metrics that we can see for this particular pipeline, everything from memory usage, disk usage, CPU utilization. We also see some alerts. We don't have any alerts right now on this, but we could if we wanted to. We also give you the ability to manage secrets and things of that nature as well. So we'll go back real quick and see if this thing finished. It should have finished already. Oh, still running, it looks like. Oh, tough. Okay, well, looks like we have a little bit of a failure here, but maybe we can show one of the ones that already ran. Should be this one here. Oof. Oh, it looks like something's cached here. Okay, let me go back and find one that I've generated in the past. So not in this one.
I just want to say I really appreciate you doing a live demo. We all know that these are not the easiest things in the world, and all had little hiccups as we try to go through things live.
Yeah.
Thank you.
Okay, maybe let's do, I think this maybe it should work. Let's see if this works. Whoops, that's not what I wanted to do. Trying to recover quickly here. See if we can show something. I think this is, yeah, okay. So this was generated by Aineko Dream at some point in the past. Basically, the example that I gave, I think I said something like create a pipeline that will ingest blockchain information from the Ethereum blockchain and then do something with it, right? So you can see that the project actually went through and interacted with OpenAI and returned sort of this README file that describes the project as a whole. Oh, oops. There we go. Describes the project as a whole a bit here. So what we want to do is, ingest the blockchain information and then store it in a PostgreSQL database. So pretty simple kind of example. It describes a bit of what we're going to do with this Ethereum data fetcher node. And then with this, okay. And then this Postgres data inserter node. And then it describes a little bit about what the pipeline looks like and maybe has a quick note about the design. This is useful if you are using this as a templating tool to just kind of see what it built. And then here's the pipeline example. So it actually went through and produced this class, right, that we discussed before, this output that we discussed before, and it looks like it wants to take as a parameter this node HTTP thing parameter, and it looks like it would connect to Infura as a data source, right? So Infura is like a blockchain data provider, and that's actually correct. I think this I'm not 100% sure, but the URL looks relatively good to me. The Postgres data inserter basically has as input this Ethereum data. Looks like it has no output, so the output will just be interacting with that Postgres server, and it looks like as parameters it'll take in DB name, user, password, host, and port. Those also seem relatively standard for what you might need to make a connection to Postgres. And then it looks like it took a pass on the information. It looks relatively straightforward. So right now, this looks pretty simple. All it's going to do is get the latest block and then produce that block to this data set. This one is going to start a connection to the server using Scicop G2. So if you're familiar with interacting with Postgres in Python, this looks more or less correct. Maybe in theory it should run, right? And so forth. So anyways, I'll pause here, but this was just to show an example of how you might develop an application using the Aineko framework and sort of get into production. So yeah, maybe it went a little bit over time that I wanted to, but I believe we have a few minutes for questions if there's anything.
I've got a few questions, but I'm going to defer to Nick to see if there's any questions from the audience.
There is one in the chat, one from me and one from Will. So Will asked, can you say more about the added complexity of real-time data analytics and event-based data compared to more typical batch processing? And he added, it looks like an awesome framework.
Yeah, totally. So, I mean, a couple of the things is I mentioned before that when you break things down into like these individual components that only have an input and output, what you might get, as you saw from that graph that I showed earlier, is like you have a lot of inputs and outputs, right? So then now instead of having just like one big data set that you're operating on, you now have like all of these individual small kind of steps. That can be difficult to reason about when you're trying to hold in a mental model of like the entire structure. So there's a lot of complexity around that. Again, the benefit of that is that you get this sort of smaller batches, smaller pieces of work in order to like actually make changes, right? So like a user that like, for example, in the example that I had here, if you want to take out the OpenAI and replace it with Anthropic, you don't really need to know all about the whole system. All you need to know is like, this is what my input data looks like. I'm going to, I need to have some knowledge about the Anthropic API. And then this is what my output data needs to look like, right? And as long as I can do that, then it becomes easy to grok the whole system. Other challenges, I think, I'll just mention a few quickly, but other challenges are around sort of stateful computation. So one thing that the Aineko framework does really, really well is manage long-running stateful processes, right? So like in the example that I showed here, basically what you can do is you can retain that entire chat window, all of the information for the chat that you're having with the OpenAI client, and retain all of that information in memory, so that if you need to make up, correspondingly new chat messages that use that same data, you have it available with you. That's not typically something that you have available to you in a sort of batch framework, right? So that represents a new set of complexities, both for kind of reasoning about solving these problems and also for managing the corresponding infrastructure that's required for putting these types of applications in production. There's just a couple, but there's a whole set of, a whole class of complexities that are generated here. But in my opinion, obviously I'm a little biased, but the benefits sort of outweigh the costs.
Great. So Rahul, I have a question in the chat, but please feel free to jump in.
No, go ahead.
So in one of your slides, you showed sort of two different data sets. You had an Aineko data set and then your data asset sort of from the rest of the platform. Can you talk a little bit about how the Aineko data sets are different?
Yeah, so what we're trying to do is basically build what we call a dataset API. So the dataset API will have, let's say, like typical CRUD operations for a corresponding data set that you might want to have. Under the hood, what you have is for each type of data set, you might want to have, or you would need to have some sort of a management API for that data set, some query API for that data set, and then some storage for that data set. In some cases, it might be a full stack solution. Like for example, with Kafka, it's a full stack solution, right? So the storage is stored inside of the Kafka logs. The query engine is basically the consumer producer model that's inside of Kafka. And then the management API is basically the Kafka broker API, right? That you can use to create new topics and so on. In a different approach, you might actually have sort of distinct versions of that where, for example, the underlying storage mechanism might be Parquet. And then the query engine that you use might be something like DuckDB, right? DuckDB also gives you a management interface, so you might be able to, connect the dots between those. But for the user, the idea is to be able to configure that sort of entire thing as an asset that you can interact with using the Aineko dataset API, right? So then the dataset API will expose these sort of like CRUD operations that are unified across all of these different types of data sets, including both long-term data storage, like I mentioned, maybe DuckDB on top of Parquet, or sort of like ephemeral or streaming data sets like Kafka.
So I think you answered my follow-up there, which is essentially the Aineko data sets then are they configured so that they will back propagate into the original data asset? So changes that Aineko makes are pushing back into your data assets?
Yeah, that's the idea. The idea is to represent them sort of one to one, right? So like
Yeah.
if you have the data asset and you refer to it, it can be dangerous, but there's like ways to get safety around it for running things locally. But it makes it actually a lot easier. For example, if you have a data asset that points to a database that's running in the cloud somewhere, the config is the same if you run it locally versus if you run it in the cloud, right? So yeah.
Okay. Rahul, I'm going to pass to you. We are at time, but we can stick around a little late.
Sure.
Sure. Hey, yeah, thanks, Carter. Great talk. Very appropriate for our audience and our focus. As you can see, this is the get your shit together, get your data shit together, meetup.
Yeah, totally.
Which is what I think data engineering is all about. And I really liked the example that I understand the fundamentals of EDA. We obviously understand EDA.
Sure.
And I liked how you tied in the LLM stuff using the prompt engineering from OpenAI to create the prompt engineer, basically, or to create the potential flow. So that's kind of cool. So I'm aware of a few different existing mechanisms that could do what you're talking about. I think you're taking a different approach. And, again, I'm going to name a few. You don't have to know what they are, but, there's Spring Cloud Data Flow. There is, in the akka world, there are a few different ones. There's Dapper.io. There is, there's all these things with the word flow in it. I don't know. I was looking for something called Cloudflow, which is the akka one, and it turned out there's a shoe called Nike Cloudflow.
Nice.
So, and then there's a few SaaS players out there in the stream processing world. And so again, I'll take my stab at what I feel like you were saying is different for Aineko, which is that you're kind of like the Heroku for your data process. You code it, you push it, it takes care of the rest of your stuff. And what else would you say? Like, what would be your closest competitor in the open source or the SaaS world, and why are you guys better? That would be the question I have.
Yeah, sure. Yeah, I think Heroku is a good example that we've used internally. Another one that we like to throw around for folks that are like either full stack engineers or have some experience with front ends is Vercel. So Vercel has a really amazing developer experience around building front end applications, and we kind of wanted to have a similar experience for data applications or event driven applications, right? I think we've been able to achieve that for the most part. To create a framework makes it really easy to build these applications and then be able to connect them through the cloud using GitOps and so on. So we have a lot of the same flavors as that. Yeah, I would say maybe like a better example than the typical sort of like, I'll call them like Airflow-esque type of approaches, right? So like Airflow is a good example of building a DAG and doing sort of batch processing and so on. A better example of like what you might compare, to Aineko is something maybe like a development platform like Temporal. So Temporal is a development platform for building sort of event-driven applications. They're really good for like workflow-based applications and so on. What we do is similar to them, except that we have data as a first-class citizen inside of our applications, right? So if you want to have connect to different data sources, have this data set API that I was discussing earlier with Nick, those are all things that are kind of don't come out of the box for free with Temporal that we help you manage, create some abstractions that are useful for that. Another example might be, another sort of early project like Modal. So Modal is an early project that basically allows you to to like very rapidly build serverless Python applications. So you can make a function, add a decorator, hit deploy, and boom, it's kind of in the cloud. I think we want to have a similar feel as that, but again, with a lot more utility and control around the underlying infrastructure that is utilized for processing the data, and give you be a little bit more opinionated about the types of applications that you can build, such that we can add more value to the user, give them more reliability and more ability to sort of scale over time, right? What we found with these sort of Lambda-esque approaches is that they become brittle over time as you deploy something to the cloud and then you make a change and it's unclear how to put all of the pieces together. And obviously AWS or some of these other tools have some diagramming tools to kind of be able to grok all of that together. But we're doing it from the ground up and giving the developer a better experience on that front.
Yeah, I mean, Vercel, I didn't mention Vercel because we tried using it for some LM stuff,
Sure.
And it times out on the free account, and then it has a limit of 10 minutes for some things, right? So again, nothing against Vercel, but yeah. And then same thing with the modal. I think they have general restrictions on how long these things run. So you eventually have, if you want to do anything differently, you still need to do something else. Right. You mentioned temporal. I think in temporal, I understand what you're talking about. I mean, but temporal does some really long running workflows. You can have a workflow that just kind of persists per customer for 1 billion customers. Whereas I like what you're describing is more of a ephemeral, long-standing processor or a set of processors, and kind of managing that graph, not the DAG, perpetually. But how is that, let's say, and I know what you're going to say, but I'm still going to ask it. This is a question somebody would ask, right? It's how is this different from using Kafka Streams or Kafka Connect or Pulsar IO or Alpaca is the one in the Akka world. A bunch of connectors in there. It does backprop. At least Alpaca does backprop.
Right.
All this stuff, right? Ultimately, why would you use Aineko? And I'm not saying this as a skeptic. I'm just saying this for somebody else that may be well, this is what I already know. Why would I go try out something new?
Right. Yeah, I mean, a couple of things. One is that from the perspective of the underlying infrastructure that you use, we are sort of opinionated right now in the sense that we do use Kafka, we do use Ray kind of out of the box, but the goal is to make those distinct. So then you give the user the ability to kind of utilize the Aineko framework, but still use the infrastructure that they already know and love, right? So if you already know RabbitMQ, why would you use Kafka? Just use RabbitMQ, right? Or if you already know, Kubernetes and that kind of experience, or Flink or something like that, why would you use Ray, right? These kinds of things. So that's one thing. The other thing that I would suggest as well is that those platforms they solve one problem really, really well, albeit they solve it really well, right? It's stream processing. It's this goal that basically you want to take, it's similar to this problem, right? But slightly different in that you want to take as input a topic, right? So if we're talking about Kafka as an example, as input a topic, do a bunch of stuff and then output another topic, right? So in the middle, there's sort of all of this ephemeral data that might be flowing through, different processes that are occurring for that stream process, and you do it live, and you can obviously do it very efficiently in a scalable manner. What we've kind of done is we've taken a step outside of that and basically said everything is kind of a stream process, right? But instead, we're going to give the user an API to the units of compute, and then give them the flexibility to say this data set is ephemeral versus this data set is not, right? In which case, what you get is kind of more flexibility in your ability to represent the types of use cases that you want. For example, the one I represented is not something that you would be able to do inside of a Kafka stream, right? You wouldn't be able to say, I want to have one node that has a long running process that's stateful, and the particular state is, a chat conversation with OpenAI. You wouldn't be able to have that sort of expressibility. With Aineko, that's made relatively straightforward, right? Just Python code snippet, put your application diagram together, and boom, you've got it flowing. That's kind of all it is, right? I think they focus quite a bit on that input topic to output topic. We're focusing more on input data set to output data set, which gives you more flexibility with the types of applications that you can represent.
It sounds also like it's just more embedded with LLM and generative AI components inherently. Like those are just sort of easier to integrate
Correct.
with your platform. Yeah.
Yeah, anything related to AI. Now, granted, now Kafka streams and so on have some, connectors for those types of things, but here, at least right now, we're built in Python, so you can do anything that you can do in Python, right? So like if you have a Jupyter notebook that has the model that you've created, and you have like some way that you sort of ingest the data, process it, and so on, you can reflect the exact same logic inside of the Aineko framework.
Yeah. I've got a couple ideas. Maybe we can shoot it around, but what to kind of showcase what you're trying to do here. So
Sure.
in the LLM world, the in the RAG world, like it's like any other AI ML conversation from 10 years ago. It's like, oh, we can use AI. It's like, okay, on what data?
Yeah. Yeah.
So in the RAG
Exactly.
conversation, it's like, oh, you can do so many cool things with
Right.
OpenAI. Like, okay, well, what about my information? So so the challenge is like, how do you get all this stuff into a vector database? And sometimes it's not just pure embedding; it's summarization, classification, and then embedding it so that it's the metadata is smarter, the embedded data is smarter. And it'd be kind of cool to see if we could collaborate on a simple data manager where you like added, XYZ and said, okay, go ahead and put this in this vector database, right?
Right.
And doing it as a streamed EDA process versus a batch process so that when there's new data, then it can, continuously get updated, right? So yeah, because I was thinking about doing like a GUI for Llama Index and what to use under the hood for the processing. And like we're like you, we don't reinvent the wheel. We're lazy. I was talking to a colleague. I was like, I think my secret sauce is I'm lazy.
Exactly. Yeah.
I mean, like
we created this whole
thing to work. Let's see what we can use, right? So
yeah, exactly.
But yeah, so for on the batch side, Airflow, and then there's connector stuff on the Airbyte world as well. But it'd be interesting to see, what exposure your connector ecosystem has, where on the source side and on the sync side, at least in the LM world. So I'll reach out to you and we'll
let's connect. Let's connect on that.
Okay. Awesome.
Yeah, sounds like a great use case. So yeah, let's definitely connect.
Cool.
So I want to thank everyone for attending our extra long data engineers lunch today. We have another one scheduled for the beginning of February. So stay tuned. You can always find out more on our meetup. Thank you, Ricardo, for your time. Thanks, Rahul, for being here. And great talk. Talk to you all next time.
Thanks, Nick.
Cheers.